start the recording anyway. The first thing that I want to do is play Let's Make a Deal with Everyone. You ready for this? Here is my deal. As you can see, these are the percentages of you who have completed your course evaluation for this semester. So far, 35% of you, 8 out of 23, you are currently beating my other class, but I issued a challenge to them as well. So here's my deal. Screen share, yes. Thank you. I'm going to remember that. Right away. There we go. I'm looking at my course evaluations page. So here's the thing. I want to ensure representativeness of this survey result. And what better way to get a representative sample than to get the whole damn population? So the 20 of you are the population for, 23 of you in this class, excuse me, are the population for this course. If at least 21 of you complete a university course evaluation by Saturday, I will give all of you 1 point of extra credit. That's a whole percentage point towards your grade. That's deal number one. Deal number two, this afternoon, you will receive an email invitation to complete a separate Qualtrics survey that I designed for this class that asks more specific questions than what the university course evaluations do. And each person who completes that will get a point of extra credit as well. So up to 2 points extra credit for your time in providing an evaluation and feedback about this class. In particular, this was the first time that I've tried the use your own data homework, so that's a question that I added this year to see how you folks responded to that. The Qualtrics survey is set up to where it tells me which email addresses have completed a survey, but it does not link your responses to your email. So it is still relatively anonymous. I will leave the Qualtrics survey open until the end of finals week, so you can take your time finishing that. University one, though, closes on Saturday night. So that's my deal. Up to 2 points of extra credit. Again, repeating for the folks who may have just joined us. If at least 21 of you complete a university course evaluation, everybody gets a point of extra credit. You get a second opportunity for another point if you complete an individual Qualtrics survey that you will get via email this afternoon. So how does that sound? Deal? Good. I value your feedback. Just a little bit about how these numbers get used. So the quantitative evaluations are used in things like merit review to determine raises. For junior faculty, they're also used in terms of promotion and tenure. But the qualitative evaluations tend not to be read as much, in part because I think they're a little bit vague, like what did you like, what did you not like? So that's why I supplement the university questions with a separate survey that's much more directed. And I do want to encourage all of you to be as honest as possible. I am bribing you to get a good response rate, not necessarily to get a good score. Let's be clear. I want you to be honest. If you are unhappy about something, I would want you to tell me about it so that I can maybe fix it or at least evaluate what I'm doing with respect to moving forward, because I plan to offer this class every spring for the next foreseeable future. So, all right, any questions on that? All right, then while I'm in Icon, we have a quiz to go over. I updated grades this morning. You also should have gotten an email from me with respect to your homework 5. So your homework 5, if you submitted it up to this point, I've graded everything that I received as of this morning. That is available for download inside the homework portal, so not inside Icon. That's the reason that I wanted you to name them in a particular way so that I could create a dynamic link to the document. So you should be able to see your score. I went section by section in terms of where, and I tried to be clear about what extra things you would need to do to get full credit. If you want to revise it, I would need those revisions by the end of finals week. There is a spot inside Icon to submit them. If you look at your score and you're like, yeah, I'm happy with this, I don't have time to get my extra 2 points back or whatever, fine with me too. So it's up to you whether you want to revise. I think that learning to respond to feedback in doing revisions is a necessary thing, but I'm also aware that you have many competing demands at this time of year, and so maybe this isn't one of them that you want to prioritize. It's up to you. But formative assessment number 6, look through your answers this morning, and it seems like most folks did pretty well. A few questions that came up, though, in terms of what people answered that I wanted to make sure to hit. So first question then, in what situations or types of research questions is estimating multivariate models via path analysis a better strategy than tricking univariate software into doing multivariate models? So to be clear, Tricking univariate software is my term for the approach of changing your data from one row per person, one variable per column, into a long transposed data set where it's one row per outcome per person. That way you can tell the model to estimate residual relationships for the outcomes from the same person, and then use dummy codes to control which outcomes are predicted by which predictors. So that's my term for that. So that is one option. Path analysis is a more general strategy. When would you want to do path analysis instead is the question. What do you think? Louder? Mediation. Yeah, so mediation is of interest with respect to computing indirect effects in particular, which is something we're going to start talking about today. More generally, anytime you have a variable that is serving the role of a predictor of some things while simultaneously being an outcome of other things. Now, technically speaking, I know how I could trick univariate software into doing that, but at that point, it's not worth it. Like, that would be a last resort kind of thing. I could make it go, but the amount of coding and trickery that it would take outweighs the benefits of doing so. At that point, path analysis is a better strategy. What else? What would be another reason? Even if you're not interested in models that look like that, when might path analysis be a better strategy? I can think of two others. If you want to compare the size of effects? Yeah, I think actually you could probably do that either way. It might be, you could do that via explicit model constraints in path analysis, or you could do that via linear combinations. What else? What about missing data? Would that be a reason? Missing outcomes or missing predictors? Yeah, missing predictors. If you do a path model strategy, which is a multivariate strategy where you can predict multiple columns, that's the difference, is being able to predict multiple columns. Then you can estimate an empty model for your predictor, meaning it's not really being predicted, you're just estimating its mean and variance, and then it becomes part of the likelihood, which allows you to have missing data. So if you're concerned about missing data on predictors and you don't want to lose cases that have missing predictors, pretending it's an outcome via a multivariate modeling strategy is a reasonable alternative. The only downside to that, then the predictor has distributional assumptions, and that matters more when you have more missing data. So you don't get everything for free in that case, but it's still better than dropping cases. What about generalized models? A few of you mentioned limitations of univariate software in that. We touched on that briefly. Zoomers, I'm watching the chat too. Awkward silence. I'm cool with that. I'll just sit here. Don't bother me any. I taught during COVID online. I can handle anything. Every grown-up meeting, by the way, that I still go to starts that way. On Zoom, everyone's just all quiet and awkward. So yeah. You were going to say? It's really good at general. It's usually not great at generalized. Where the problem comes in is when you have outcomes that need some kind of over-dispersion parameter. So if you have, say, binary outcomes where there's nothing extra that needs to be evaluated, just fine. If you have ordinal outcomes, it constrains the submodel intercepts to be the same across outcomes. There's no easy way to change that. Likewise, if you had a count outcome or a binomial outcome where you needed over-dispersion, like some kind of stretchy parameter for extra variance, it assigns the same stretchy for every outcome in that column because it's treating the column as one unit. So that's less than ideal if you have different outcomes that might need different degrees of stretchy over-dispersion parameters. Whereas in multivariate models, you can predict each column separately with whatever type of model each column needs. So that would be another reason. Is there any situation in which you might prefer tricking univariate software? A couple of you mentioned this, I think.
Like more simple longitudinal stuff where it's just like one thing. That's not specific, but
So the answer was more straightforward longitudinal stuff where it's just one thing.
Yep,
That
that's
is
my answer.
That's your answer? Final answer?
Yep, final answer.
Final answer. Okay, that is correct. That is one option. Like repeated measures or anything where it's like the same outcome conceptually, you just have multiple times of it or multiple conditions of it. Then what is of interest are differences across time or conditions. I think it's easier to think of the model that way in a univariate framework. That might be one reason, and in that case, you wouldn't have mediation or outcomes that are both predictors and outcomes. And you would use random effects to control different variances across outcomes. There's one other situation, type of data in terms of sample size. We touched on this very briefly. What kind of likelihood estimation? Small samples.
You can do t-tests.
Yes.
You can't do that in the path analysis.
Yes, path analysis software by and large is regular flavor maximum likelihood with walled tests that do not use denominator degrees of freedom. So the same thing that you may have learned back in intro stat about when to use T versus Z is applicable here. T adjusts for differences in denominator degrees of freedom, which is number of people minus fixed effects. It matters more if you have smaller samples. So path analysis is designed for larger samples. If you have a very small sample, then you might want to stick with univariate software where you can have what is known as residual maximum likelihood, which is the same thing as ordinary least squares, and T's and F's rather than Z's and chi-squares for your significance tests. So that might be one situation. And someone will say, but what about Bayes? And I'll say, what about Bayes? Bayes is supposed to fix small samples, but not necessarily. What it would allow you to do is to have priors that are a little bit informative to better control what the parameters become, but then you'd have to justify that. So maybe not a panacea for everything. All right, any questions on that? Comments? All right, moving on. Number 2, total versus model degrees of freedom. I'll phrase these as forced choice alternatives. Does this have anything to do with people, a number of people? It does not. Does it have anything to do with number of variables? Yes, it does. Yeah, so total degrees of freedom is basically the number of pieces of information you have with which to estimate your model, where pieces of information are the means of your variables, the variances of your variables, and the covariances of your variables, if you're assuming everything is multivariate normal, which is the situation we've talked about up to this point. So that's total. Model degrees of freedom is another multiple choice. How much you spent out of those, or how many is left over? Model degrees of freedom, spent or left over? Spent meaning estimated. You can think of it as like money. Got one vote for leftover from the Zoomers. Another vote for leftover. Now everyone's jumping on the leftover train. That is correct. Leftover, meaning that you haven't estimated every possible parameter that you could have. Usually what that means in the context of path models is that there are pairs of variables that do not have direct relationships, either as slopes or covariances, but they have implied relationships because of the rest of the model. There's vocabulary words to that. If you have degrees of freedom left over, meaning that your model has positive model degrees of freedom, what is the word for that? Underspecified I will take, but not the word that was in my head. I would say that's a synonym. It starts with an O. Over, not fitted. Over dispersion is a different word. That means extra variance relative to the mean. Over, the next letter is I. Yeah, over-identified. Yes, so we have under-identified, just identified, over-identified. Under means broken. You are trying to estimate more parameters than is logically possible. Negative degrees of freedom. Just identified means you spent them all. You broke even. Over-identified means you left something on the table. So you can think of it as you've overlooked certain pairs of variables, or you've under-specified all possible relationships. I will take that as a synonym. So when do you need to worry about testing model fit, or establishing that you have adequate model fit before interpreting your results? Which of the three? Under, just, or over? Over, yes. So if you leave stuff out, the onus is on you to show that that wouldn't have changed anything if you put it back in. That whatever you're missing would have been as close to zero that it's good enough. Just identified means it fits perfectly because you spent everything. Like, you cannot be wrong. That is what I tend to recommend as a strategy for path models, because then you don't have to worry about model fit. It is perfect. Question?
Why wouldn't you just always just specify it? Like if you have to prove that it's okay.
A lot of times people want to make an argument about how things relate to each other. So like if you think of like a chain of variables, and it's like, well, this is related to this only because of this, 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 and this in the middle, they're lacking the direct relationship. And so that lack is a testable hypothesis. So it's consistent with a theoretical viewpoint of how these things relate to each other to leave it out, but you have to make sure that you haven't screwed up the rest of the results by leaving it out. Yes.
Is that somewhat related to parsimony? A more parsimonious model would be over-identified?
Yes, a more parsimonious model would be over-identified. Parsimonious generally means enough stuff, but not anything extra that you don't need. So just identified is not usually parsimonious. The reason that I say just identified is a reasonable strategy is because then you can't be wrong with respect to your conclusions being subject to model fit. The model has to fit if you spent all the things, but it would not be parsimonious in that case. So that's the trade-off. Yeah, I don't think I asked a question about that, but in terms of fit, are the fit indices that you get going to agree with each other all the time? Another multiple choice question. They will not necessarily. Some of them are, how much worse are you than perfect? How much better are you than the worst possible? There are two different flavors of them. And so to the extent that they use different points of comparison, they may not agree. If I get a likelihood ratio test for how well my model fits and it's non-significant, good news or bad news? If my likelihood ratio test is non-significant, meaning my p-value is greater than 0.05 for comparing my model against the perfect model, good news or bad news for non-significance? We got good question mark, good, capital good, good news. The consensus is good? A lot of abstains, looks like. Yes, good news. So the test of model fit that you get on your output is how much worse is your model than the perfect model. If it's not significant, that means it's not worse. It's good enough. Meaning the things you left out for parsimony, cool. You didn't need them. They would have been zero if you put them in. The relationships that you have do a good enough job of recreating the relationships that exist in the data. You're not overlooking anything. Other ones that are relative to perfect are MSEA, SRMR. Both of those you want to be as close to zero as perfect as possible. The ones that are relative to better than the worst are the comparative fit indices, CFI, TLI, NNFI. I think that's all the letters I know. There's a bunch of them, point being. But that's sort of the two families. Worse than perfect, better than the worst. Which I think as we approach our last week of the semester here, happy garbage day, by the way, I've got my merch on. Unfortunately, it's still cold enough to where I need long sleeves, which I am not happy about, but such is life. This idea of worse than perfect or better than the worst, I find this to be useful philosophically in thinking about how far we've come. Right, you can look at, the leaders in your field who publish, 1 million papers and have 1 million citations, and you can feel bad about yourself because you're not there yet. Right, I still do this, right? I look at like people that I aspire to be like and think, how did they learn all this stuff? Or how can they do that? I don't know how to do any of this. I don't know anything. And it's real easy to like get down on yourself because worse than perfect is a really difficult thing to achieve. Not worse than perfect, rather. But if you look at it from the other way, at the beginning of the semester, did you know what a logit is? Maybe you've heard of it before, but you're like, I don't know what the hell that does. Did you know what a probit is? Did you know what overdispersion means? Did you know how to make R do any of this stuff for you? Or stata for that matter, right? So if we think about like where we've come from, that's a positive thing. Like, yeah, I'm not as good as Don Hedeker or other people that I really aspire to in the field, but you know what? Relative to like 18-year-old Lisa, I've come a long way. So the comparative fit index of my life, right? How much better am I than the worst I started point? Nailing it. A little bit of philosophical digression here, but it's good to stop and look back at where you came from and feel good about that as a point of comparison. I imagine after going through this class, and in particular me beating the crap out of you with interaction terms and model implied, simple slopes and all that kind of stuff, that if you looked back at when you first learned that stuff, you'd be like, oh, I can do that, that's no problem. Once you take advanced classes, the stuff that you had before suddenly becomes easier. Relative to worst possible, we're all doing excellent. Amen. Last one. How is it possible? 2 question marks. I would have used interrobang as my other favorite punctuation mark, but they didn't have that as a choice. Interrobang is the one that has a question mark with an exclamation point in it. It's like the WTF symbol, is the way I think of it. How is it possible? I'll just do an interrobang with my voice. That you can achieve excellent absolute model fit, yet have none of the direct paths or covariances be significant. How is this possible, folks? Not a multiple choice question this time. Pretty much everyone wrote down the correct answer. So just read to me what you wrote.
I wrote like just because it shows a relationship doesn't mean that it's a strong relationship or a robust relationship or like meaningful.
Mm-hmm. So strong or robust or meaningful, the word I would use for that is effect size, right? Like what is the strength of prediction, strength of relationship among these things?
Or like could you say like magnitude as well, like something that has magnitude?
A relationship would, have magnitude, sure. Does excellent fit mean that you have excellent effect size? There, back to multiple choice. It does not. What does excellent model fit mean?
Means that your model predicted things well. Like it's about like the model's ability to predict the outcomes, right? As opposed to to reproduce.
Yeah, I would stay away from the word predict because that heads into something that sounds like effect size, but reproduce would work. Or recapture, recreate, all of those kinds of words. Fit means that the relationships that are in your data have been replicated, reproduced, captured, all of those words by the model. Like your model is faithfully reproducing the patterns. Effect size is, okay, what are the patterns? And is there anything worth modeling? So if you have a bunch of variables that have nothing to do with each other, You can have a path model that fits very well because it has perfectly reproduced the non-relationships among your outcomes. Or you can have a bunch of variables that are very highly related to each other, and you can have a model that perfectly reproduces the strong relationships among your outcomes. Perfectly reproduces is the idea of fit. What is being reproduced is effect size. Two different things. Why is it that we've never talked about absolute model fit in this way up to this point in this class? Like, you didn't have to check the CFI and RMSEA of your regression models. That wasn't a thing. Was I just being nice to you, or is there a reason? It's all univariate? Yeah. Yeah, so if I only have one variable, what are the summary statistics to be reproduced? Mean and variance. That happens in the empty model. Done. So it fits perfectly if you fit a univariate analysis. That's not a consideration. It's only a consideration when you're talking about the relationships between variables. Because generally speaking, each variable gets a different mean and a different variance as part of the model via intercepts and residual variances, respectively. So this is only a concern in multivariate analysis, point of the story, not in univariate analysis. That's why you didn't have to worry about this. And if you don't report fit statistics because your model is just identified and reviewer 3 is like, hey, where's your fit statistics? What do you say back?
It's just identified, so it fits perfectly.
That's it. We didn't report them because they fit perfectly, but sure, I'll give you a table of zeros and ones if that's what make you feel better. Yes, just identified means it fits perfectly as a consequence of the fact that you haven't left anything out. Ta-da! Any questions or comments? All right. I checked my own recordings to see where we left off last time. Because like you, Thursday was a very long time ago. And I realized that we haven't talked about Model 4 in Example 5 yet. So that's where I wanted to pick up. So just a brief reminder of the story for these data. These are real data. We have attitude scores from moms, dads, and kids of intact families. We're predicting them with the gender of the adult child, predicting their score. We have the education of each person. And I'm looking at this going, this is a typo. This should be dad here. I'll fix that later. I never find the typos until I'm in front of you. It's amazing. Each person's education predicting their outcome. We had dad's education predicting the outcomes of the moms and the kids. And then this is the new part that we had discovered we needed based on an analysis of local misfit. Would it be helpful to re-go over local misfit, or do you feel good about that? Or just review? Feel good about it? Just review. Okay. So the idea is that you've got your perfect model on the one hand, what the means, variances, and covariances are in the data. You've got the reproduction from the path model you fit. So the idea of local misfit is element by element. How far off are you from what the data say to what your model says? And you don't have to figure that out. The software will do it for you. So for instance, here is a piece of M+ output on the preceding page, this is 17, that says estimated model and residuals. So they're using the word residuals here in a slightly different way than we've talked about them. Normally when we talk about residuals, it's with respect to the predicted outcome. So like how far off is your predicted outcome from your real one? In this context, it's similar, but predicted is relative to the summary statistics of your data. So how far off are the means, variances, and covariances in the data versus what your model says, where it's observed versus estimated. So here are the offnesses, I'll just use that word, discrepancies of what the data say and what the model says with respect to the means, because each of the outcomes got its own intercept. These are fine. Likewise, on this covariance matrix, the diagonal are variances, the off diagonals are covariances. The diagonal is pretty much fine because each variable got its own residual variance. And most of these are fairly small, not perfect, but small, except for the ones that I've highlighted here. These are indicating that our model is off. So we are under predicting the relationship between dad and mom, dad marital and mom ed, and mom marital and mom ed, and kid marital and mom ed. And notably, this one is already in the model. It's just not right yet because we're missing these other ones. So this is an indication that you shouldn't interpret what you have until you're sure that your model actually is faithfully reproducing the patterns in your data. And we talked about model constraint means that these things don't show up. So the model constraint section I had to shut off to get this section of output. These are modification indices. Remember these idea? These are the cheat codes. This is the software trying to help you fix it. Some of these make 0 sense. So the way to read these table, MI is modification index. What that means is this is how much your chi-square test of misfit would improve if you put this new term in your model. This is what it would be. This is the standardized version of what it would be. So it wants mom marital to be a predictor of dad marital. Well, that's a dumb idea because this is already in the model as a covariance. So if I actually did this, my model would be under-identified because then I would have 2 connections between one pair of variables. So that's a dumb. This one, though, it wants me to have mom's education predict dad's marital, and it predicts that most of my misfit will go away if I do that. So that's, I think, a reasonable thing that we could do. With statements in M+ are covariances, on statements are regression slopes instead. So it was on the basis of this diagnostic work that I figured out how we should fix the model. Let mom's education predict the other people's outcomes as well. So that's what I added here in the yellow. So to give you your full suite of choices with respect to path models, here is, this is the univariate version of Stata. So this is a model that I could do either way. So for completeness, I showed it to you both ways. So this is Stata mixed, in which the outcomes are all stacked in one column using long data. Here is the same thing in R, the univariate approach using GLS, where I have all of the new fixed effects in here, and we're just letting all the outcomes have different variances and different covariances for their residuals. Here is what it would look like with respect to path modeling software then. So Stata, I'm using the SEM package, which stands for Structural Equation Models, and the new effects, as I've indicated in the comment, are right here. So now mom's education predicts not only her outcome, but dad's and kids'. The rest of the model is as before. These are examples of how to compare test differences in slopes. So Erica, your comment earlier about testing differences in slopes, this is how you can do it in path models too. It's literally the same linear combination idea. The only difference is that you have to access what it's being called inside the software to know how to do it. Here is M+ code to do the same thing. So we've got new regressions I noted here, this line. So in M+, you can stack up your outcomes on the left-hand side of the on, and you can stack up your outcomes on the right-hand side of the on. The reason that I separated these is so that I could be clear what my labels were referring to. So these names in parentheses are labels for each of these slopes that I can then use to do math. So then differences between slopes can be done as linear combinations via model constraint here, where you create a new name for each difference and then you ask it to figure out what it is. And in R, a few of you have already sent me questions over email related to homework 6. Note the quotes. Quotes are very important. So if this breaks and you're not sure what happened, and some of this is in black font and some of this is in green font, check your quotes. That means it got off balance somehow and it's not reading it. So syntax 4 is one object that contains all of these lines of code. So you tell it what kind of model you want, and then you feed that as an argument into the function for lavaan. There are multiple functions within the lavaan package. I'm just using the base one because that's all we need for this context. Here are the new regressions, which I have indicated with a comment right here. The rest of this is asking for all the same pieces of output that the other programs are asking for as well. In lavaan, I want to draw your attention to the fact that there's two different columns here of output. The left-hand column is for regular flavor maximum likelihood. The right-hand column is for the robust version. And the reason I get both of those is because I asked for it, I think. No, it does it anyway, it looks like. So ML versus MLR. In your homework, I believe I told you to use the regular version, right? That sound right? Because that way differences across packages would be minimized. But what it ends up happening is you end up with this difference right here, the scaling correction factor. That is an indicator of how far off from multivariate normality your data are, and it's used to correct the fit statistics and standard errors for deviations from normality. When your data are perfectly normal, this scaling factor goes to 1, and it simplifies to the ML column. So you're not hurting anything in practice by asking for the MLR version. In Stata, there is just robust standard errors instead. It doesn't correct the fit statistics, but it does correct the standard errors. So at this point, blow this up here a little bit so we can interpret the fit first. Test statistic, as I have noted in the comment here, this is the difference in -2 log likelihood between the perfect model, which is known as the saturated model, and ours. So the chi-square value for the test statistic is 1. Degrees of freedom is 4. What does that mean? This is model degrees of freedom. The fact that it's 4 tells us what about our model? Spent or left over? Left over. So that means we could have put 4 more things in our model, but we didn't. And I know what they are. We don't have the effect of kids' gender on the parents' attitudes, that's 2, and we don't have the effect of the kids' education on the parents' attitudes. So those are the 4 that we left out. The fact that this model p-value is very much non-significant means that what we left out is functionally 0. So the model adequately recreates the associations among these variables, even if 4 of them are not specified for every pair of variables. So this is good news. Model test baseline model. Do we care about this? Yes or no? We do not. This is a comparison of worst possible to best possible. It has nothing to do with us. Ignore it. Comparative fit indices. These are how much better are we than the worst? We are awesome. We want this to be as close to 1 as possible, and some of these do indeed go over 1. Likelihood and information criteria. These values only have meaning relative to other models. So you can't look at -332 and have any idea what that means out of context. Another thing that came up in a couple of your projects, this value only has meaning for models that are estimated on the exact same sample as well. So if you specified a model with some predictors, looked at the log likelihood, and then you added new predictors that had missing data, which made your model sample smaller, this is not comparable anymore, because this is literally the height of the sum of the observations, and the sum has to be over the same entities. So you can't compare these if the cases are not exactly the same. Same with AIC and BIC, because the way that these are computed is with -2 log likelihood as the primary ingredient, and then these are adjusted for the number of parameters. So all of these things are specific to this set of outcomes in this sample. You can't compare across other samples or other types of outcomes. RMSEA and SRMR are how much worse than perfect are you? So the fact that these are 0 is very good news. So now we can look at what we found. So then in terms of what would go into a table, first off, never ever paste output into a table for a manuscript or a presentation. I think several of you did this because you ran out of time and you're like, here, this is what I'm interpreting, which is fine. But no, we need to format this. This also contains more information than what you would reasonably need. So for instance, the unstandardized estimate and its standard error, if you report these two things, which you absolutely should, you don't need z-value. Because estimate divided by standard error is z-value. And z-value is only used really to get p-value. So you could either do p-value as a column or you could do stars, or bold stuff that's significant. I like to do bold because then everything stays aligned. Confidence intervals, I tend not to bother with these because, again, these are computable if you give them the standard error. But some journals really want you to have confidence intervals, so Godspeed. These are two different versions of the standardized solution. Standardize all is usually the one that you would want. So you would want estimate, standard error, P as a column or as some kind of formatting, and then standardized. That's what would go into your table. So these are all the slopes where each outcome to be predicted is listed, and then the predictors of it are listed underneath. So essentially what we have is 3 separate regression models being estimated simultaneously to predict our 3 outcomes. Covariances among the residuals of the 3 outcomes, intercepts for the 3 outcomes, residual variances for the 3 outcomes, and then the R-square for each outcome. And then finally, the slope contrast that I asked for as linear combinations. Then we get down here. These are the discrepancies. So this is the residual output from Levon that tells you how far off the reproduced set of summary statistics is relative to the perfect model. And these are all off just a tiny little bit. The fact that the model fit is good means these are close enough to 0 that we can feel good about that. So then, here's some words to describe the findings, and here's the picture. And since I printed this handout, I posted it rather, I added this box because I realized I forgot the curved arrows that would go between the boxes here. So that's what it ends up being. Now we're done with this handout. Okay, questions on that?
Lisa, I have one in the previous page where you have the linear combinations.
Yes.
The scale of those slopes in the model.
These ones?
Yes, exactly. So those differences.
Mm-hmm.
Those differences are using the original scale of each
Yes.
one.
Yes.
So if we have different scales for each variable, how can we interpret those differences?
Yes, thank you for the question. So these comparisons of the slopes predicting, so this is the difference in the effect of dad's education and predicting the kid outcome versus the mom, the kid versus the dad, and so forth. These are all unstandardized, meaning that the only way that they make sense is if the 3 outcomes to be predicted are conceptually on the same scale. So because all 3 people answered the same set of questions with the same possible range, I would consider that to be the same scale conceptually. But numerically, each type of person rather, might have a different mean and variance, meaning they're not exactly on the same range, but the possible range. So if you were predicting outcomes that are on completely different scales, this would not make sense to do. You would have to either standardize them ahead of time so that they are on the same scale, or you would have to ask for linear combinations of differences of the standardized slopes, which would require more work in terms of the code to do that. Basically, what you'd have to do is compute the standardized slopes as linear combinations, standardizing them yourself, and then get the differences. So yes, all of this is predicated on the idea that these are on a comparable metric, such that differences across slopes would be a reasonable thing to ask for. So thank you for bringing that up. I realized I forgot to say that. So for those of you who've started homework 6, which is try your own path model, you should be able to get through most of it just based on the examples in here. What we haven't talked about yet are indirect effects. I will warn you that even though indirect effects can be found with your calculator by literally multiplying the two direct effects that go into it, that may not give you the right answer because the results don't have enough numeric precision to get to 3 decimal values, 3 digits after the decimal, let's say it that way. So I want to teach you how to get the computer to do that math for you. It is easy in path analysis with standard multivariate normal variables. It is slightly less easy in other kinds of path models, and so I'm going to show you an approach that generalizes to all different kinds of mediation analyses. All right, switching gears a little bit then, let me pick up with slide 40. Let's talk a little bit about mediation and indirect effects. Just a little bit though. I've got more stuff in here than what I care to spend class time on, just for more of your reference. So mediation versus moderation. These are words that often get used in the same sentence. Like IES, when you write grants, one of the things that you're supposed to explicitly address is mediators and moderators of your effects, as if those are the same thing, but they are not. So mediation is the idea that the intermediate variable is an explanation for why the other variables are related. So like logically, you're saying, no, your level of x causes where you stand on m, and where you stand on m causes your y. And once you factor in that relationship, x and y have a different relationship than they do before factoring that in. So said differently, mediation is all about how the unique effect of x predicting y differs after controlling for m. Does that sound like anything you're already familiar with? Unique effects of predictors after controlling for stuff? Yeah, I'll take regression for 1,000, Alex. That's what we already know how to do. So this is basically a new set of vocabulary, terminology, and procedures for addressing the same kind of question. So this is, functionally speaking, focused on the extent to which x predicts y differently after controlling for m. The only difference is that we can have x predict m as a directed relationship rather than just adjusting for the covariance between it that is used to compute the indirect effect, or the unique effects. So that's the idea of mediation. Moderation is a different thing. Moderation is interaction. So in this type of diagram, which is a very common way to represent moderation conceptually, what you're saying is that the relationship between x and y differs as a function of your level of m. So maybe x to y is stronger for people who are high on m relative to low on m, or something like that. So the proper way to describe this kind of model would actually be like this, where you have x and m as main effects. Their interaction would be depicted as a separate variable, the same way that it is listed in your code when you make an interaction term, and then all three of these things predict y. So if I have something like, let's say, chronological age, could that variable possibly be a moderator of an effect? Like, could the relationship between two things differ between old people and young people? Sure. Can age be a mediator? Could this m be age? We got one vote for no because of temporal order issues. We got some question mark expressions. Now I say this because someone once wanted my help with a grant where they had age as a mediator. What did I tell them? As nicely as possible, no. Because for that to make sense, you'd have to say X causes you to be older, and the fact that you're older causes you to respond to on Y. The only thing that causes you to be older is the calendar. Or maybe your kids, I don't know, but we're talking biological age, right? Not, feels like age or something like that. None. No. The things that logically cannot be outcomes cannot be mediators. Nothing can cause aging, just the calendar. But age could be a moderator. Certainly it could. So the big deal with mediation is focused on how the relationship between two variables changes after you adjust for other variables. That's the big picture. The classic way that people describe this involves these letters, and pretty much the world has agreed on these letters. You will see diagrams that look like this, labeled as such, where ABC, C is describing the original relationship between X and Y. C prime, or C apostrophe, is the different relationship after you control for M. How X predicts the mediator is labeled A. How the mediator predicts Y is labeled B. So A times B is how the model predicts the relationship between X and Y. So if you follow the logic of path diagrams, A multiplied by B, what these slopes end up being is called the indirect effect. And back in the day, there were debates about how to best assess this, because some people were like, well, if you want to know how different this relationship is between X and Y, why don't you literally take the difference? What was it? What is it now? What's the difference? And other people were like, no, you need to multiply A times B because that describes the reason the relationship is different. And it turns out that if you have multivariate normal observed variables, those things are algebraically equivalent. They give you the same answer. That is not true once you step out of that simple case. So in latent variables, in generalized models, in multi-level models, that's not true. And where I think the literature has landed is that A times B is the way to go. That generally gives you a bigger estimate. So you can multiply A times B on your calculator, but you can ask for it within the software, and that's a better option. So in terms of what is logically guiding this mediation process, back in the day, Barron and Kenny were some of the first people to lay out the logic of this. And the way they did it was a series of stepwise regressions. So we fit a regression with M as the outcome and X as the predictor. We fit another one with just Y as the outcome and X as the predictor. And then we fit a third one with Y as the outcome and X and M as the predictors. And then we do the math to figure all of this out. And the reason that they did it this way is right here. See this year, 1986, before most of you were born, I think, is because that was the choice then. That's what people could do. Nowadays, we can do path analysis on our phone. Like seriously, you can get to like RStudio online, like as a website, and do your homework on your phone. Barron and Kenny did not have phones. They had 8-track players, and they had mainframe computers with punch cards and things like that. So they laid out a series of logical rules that had to be followed for this to make sense, and since then, folks have adapted some of the rules. So an old rule that can now be broken, relative to what was initially formulated, is that X and Y have to be related to begin with or game over. That is not true. The way that mediation used to be described was predicated on the idea that X and Y have a relationship, and the goal is to make that relationship go away after controlling for a mediator. So like positively significant to 0. That would be considered full mediation. Whereas if it's positively significant, say a standardized path of 0.5, after you control for the mediator, now it's down to 0.3, but it's still significant. People will call that partial mediation. Well, that's only one possibility when you think of it from the lens of C and C prime just have to be different. So it could be that it starts out positive, it goes to negative. Could be that it starts out 0, becomes positive. Could be that it's way positive and now it's less positive. Different is all that it needs to be. So you can look for mediation even if there's no direct bivariate association here. It could differ when it comes to its unique association. Old rules that probably do still hold: A must predict M and M must predict Y for this to make sense. Because mediation happens through the mediator, if these relationships aren't here, then it wouldn't make sense to judge the difference in the C versus C prime. So, a whole lot of literature about how to test significance of this indirect effect. I'm sorry, but I just don't care. I've tried really hard to care about this and I just can't. But there's a whole lot of people that do. So here's a little bit about that. Turns out just using the regular approaches is not a good idea because the sampling distribution of this multiplied variable is not normal like we're supposed to be. So people fight about this. They've settled on the idea of bootstrapping because it doesn't depend on any sort of assumption about the sampling distribution for the indirect effect. And then people are like, well, what if we bootstrap it differently? And then there's like a whole line of research about different kinds of bootstrapping. I think when I built these slides, this was where they had landed on something called a bias-corrected bootstrap, but I'm not entirely sure, to be honest with you. I just don't care. The reason I don't care is because every time I've done one of these things, the result is different in like the third decimal place with respect to the p-value, and it hasn't changed my opinion. So I'm going to show you what is known as the Sobel test, which is what is directly provided in the output from multiplying the coefficients together. Know that some people may have a problem with that, and that if you are on a borderline case of significance, maybe you go to the trouble to do all the bootstrappy things. If you're in a model that doesn't have bootstrapping as an option in your software, you can bootstrap the estimates, and here's a calculator on Chris Preacher's website. He's sort of the mediation guru and has published a whole bunch of stuff on this topic. All right, there. Stopping the slides for now and switching to the example. So this is example 6a. This is a true story. I told you the beginning of the story. This is a former colleague of mine at the University of Nebraska, Sarah Gervais. She is a social psychologist who studies gender issues, and she had done a manuscript that had like 30 different regression models, and the reviewers were like, oh my God, just make this a path model. I can't follow this. And so she asked for my help to do so, and this is what we came up with. So in this story, and here's the paper, I think I put the paper inside the download folder. She has a variable of mindfulness, and then she has 4 candidate mediators, and those are supposed to affect the relationship to which mindfulness predicts warmth towards feminists. And you'll note that I have in parentheses X, M1, M2, M3, M4, and Y, because in my head, all 4 of these variables sounded like the same damn thing, because I'm not a social psychologist. So these are subtleties that are lost on me. So whenever I am dealing with other people's data, I usually relabel things in a way that makes sense. And so in the corresponding code, you will see X and M and Y as part of the comments so that we can, and the labels, so that we can follow the progression. So what's not in this picture that is in the model, by the way, are residual relationships among the mediators. Because as drawn right here, this model says that all the mediators are independent of each other. All the pairwise associations are not here as directed slopes, whereas they are for everything else. So that's one thing that is in here that's not in the picture for clarity. Her original hypothesis was that this mediation process would look different for men and women, and these are all college students that she's using as the subject pool here. So here's the data. This is the correlation matrix of these 6 outcomes. The correlations for men are above the diagonal, and the correlations for women are below the diagonal. And along with the original means and variances, this would be all you need to actually reproduce this analysis yourself. You don't actually have to have the original data. You can work on the model from just a summary of the data, because this is essentially the saturated model. This is the best model. This is the answer key. So we can see how any combination of model would compare relative to this. So here is the model in which we are not distinguishing between men and women. First in Stata, SEM. So I've got all the regressions here. Mindfulness predicting warmth, X to Y. That's the first layer. X to the mediators is the second layer. The mediators to y is the third layer. This is something new right here, which is also something I asked you to do in your homework 6. Means and var for mindfulness. This is bringing the X predictor into the likelihood so that we can have missing data. Functionally speaking, what I'm asking for is for an empty model to be estimated for it, where I have an intercept and a variance left over, and that's it. I'm asking for residual variances for all the things that are otherwise predicted. This option allows all possible covariances between pairs of variables, so cove structure with unstructured, meaning let everything be what it wants. Full information maximum likelihood with robust standard errors. SStat gives us direct, indirect, and total effects, and then here is how you make it do math. So in Stata, LinCom is for linear combinations. NLCom, can you guess what that stands for? Nonlinear. So you can do more kinds of things if you have NLCom, and in this case, I'm making the indirect effects. So this is the name of the A path from mindfulness to internal whatever. This is the name of the B path from internal whatever to the outcome warmth. So this is how you get indirect effects out of your software. You don't have to get your calculator out. It will make the coefficient, figure out what the standard error should be, and then do the Sobel test, assuming that that indirect has a normal sampling distribution and give you a p-value. Another thing that people like to ask for are total effects, where you sum across all the indirect effects. I asked for that literally as each indirect effect added together, along with the last direct effect from mindfulness to warmth. And then these are the total indirect effects just by themselves. I'm asking for standardized solution and model fit and R-square per variable. So this is the missing piece that you have not yet seen that will allow you to complete your last homework, requesting indirect effects from the software. Any questions from the Stata users on that? All right, our users, this one's for you. So I'm writing out everything, even though you don't technically have to, so that you don't have to try and figure out what's a default and what's not. First thing that we have here, these are all the intercepts and residual variances. Single intercept with a 1 for, or single squiggle with a 1 for intercept, double squiggle for the variances. In the comments, I have labeled what's happening here, and then I have labels attached to these for what the path is actually meaning. X to Y, X to my mediators, and then here are the mediators to Y. So warmth is predicted by all 4 of these things in one line. Here's all possible 6 covariances among my 4 mediators, and then here's how I made indirect effects in R. I named it X to M1 to Y is X to M1 times M1 to Y, where those names are given in parentheses up here. So it's using the names as a placeholder for what that slope coefficient is going to be so that it does the math on the resulting slope coefficients. Then we also have total direct and indirect effects and total indirect effects summed together, because some people care about those. All right, so most of this we've seen before. Single squiggle for intercepts, double squiggle for variances or covariances, and single squiggle for regression pokes, paths. Regression pokes, I like that better. Hey, you're predicted. It's a poke. It's 3:07, I'm going for levity. All right, reviewer 3, this one's for you. What does that mean? Model test user model. Sounds like ChatGPT wrote that. Test statistic, exactly 0. Degrees of freedom, exactly 0. What's it mean? It fits perfectly because there's nothing left over. Model degree of freedom 0. We spent everything. In other words, what is the word that goes with this? Starts with a J. Just identified. Yeah. Meaning spent everything. Has to fit perfectly. There's nothing left. We didn't leave anything out. So everything else, then, perfect. As good as it gets. And yes, that was an actual reviewer comment on this paper. Because we did not report fit statistics that were perfect because they were irrelevant. So I had to add, it's just identified, meaning that the fit is perfect. So here are all of the relationships. We have a direct relationship between mindfulness to internal whatever. So you would interpret these the same way as usual. These are just slopes. They're called direct effects in this context, but they're just slopes. So for every 1 unit change in mindfulness, internal whatever goes up by 0.33. For every 1 unit change in mindfulness, hostile whatever goes down by 0.196. And it looks like 2 of the mediators have a direct relationship in predicting warmth after controlling for mindfulness, where hostile whatever means less warmth and internal whatever means more warmth. And yes, if I did not have the PI's guidance, that is exactly what my results section would sound like. Internal whatever, external whatever. That's why they have to name the variables. And I commented on several of you to try and avoid synonyms, right? Because especially when you have like 4 different kinds of sexism that are carefully named as different things, do not change that naming convention or there's no way your readers are going to stay with you. So to me, it's M1, M2, M3, and M4. To her, it means something completely different. Covariances among the residuals. These are the intercepts for each variable. These are the leftover variances for each variable. And R square, cough, cough, homework question. R square is not given for mindfulness, even though it has a variance. Why is that? Mindfulness is the X variable at the beginning of our chain. Why doesn't it have an R square if it has a variance like all the others? It's a predictor, but it's in the likelihood. I know that because it has a variance. Why don't I have an R square for it? You're on the right track. Just carry the thought through. It's an outcome with air quotes according to the model. Is it really an outcome? Is it being predicted by anything? No, so what's its R square? None. It's not being predicted. So either the software will say a 0 or it will just leave it out. Here's my indirect effects. It looks like I have a significant indirect effect through my first mediator and through my third mediator, but not my second or my fourth. M+ code is next. Most of this is familiar to you with the exception of just a few pieces. The first thing right here, bring X into the likelihood by estimating its mean and variance. So I'm asking for mindfulness to have an intercept in the brackets and mindfulness to have a variance. That turns it into an outcome so that it can have missing data. Then the rest of this, intercepts and residual variances labeled for completeness. Then we've got all the slopes for X to Y, X to M to Y. All possible covariances can go on one line with width. And as I mentioned in your homework instructions, what if I wanted one of these to be shut off at 0? To shut off a covariance instead, at 0 on the end of it. In R, it's *0. In Stata, it's at 0 as well. So when you write something, it's implied that you want it estimated unless you say otherwise. Model constraint, this is the generic way to make indirect effects. There are other ways that save typing, but this way will work for more different kinds of models. So I'm making 4 new indirect effects here, literally as the multiplication of the path from x to the mediator and then the mediator to y for each of them. The easy way is right here. Model indirect, you do the math. And it will. So warmth is the outcome. Ind means find all the ways that connect to warmth from mindfulness. So this will do everything that I just did in code for you. The reason that I did it both ways is because this model indirect only works in certain cases. Doing the math yourself via multiplication always works. And all the results are the same. Perfect model fit because it's just identified, and indirect effects for the first mediator and the third mediator. And then I've highlighted the ones that show up, the totals down here, and then these are all the specific indirect effects that it figures out for you. And that's a good place to stop. Not just because it's 3:14. That's just a coincidence. All right. Questions before we call it a day? You can now finish your last homework. And if you're like, I don't even have time to think about that right now, that is acceptable as well. It is not due until the end of finals week. And I have office hours tomorrow as usual. During finals week, I have my regular office hours plus office hours when I was going to be teaching anyway. So from 12:30 to 3:30, Tuesday, Thursday. So 9 hours of office hours during finals week if you need help to catch up, okay? I want everyone caught up and happy with their performance in the class by the end of finals week. That's the goal. All right, then let's call it a day. Hope to see you Thursday for our last class together. Let me know if you need anything. Thanks for being here. Bye, Zoomers. Bye, Zoomers.